Okay, so welcome back, and we will continue our discussions on chapter 11, which is regression. Yeah, I already, told you a few times, so it's a quick review about where we are. So, as I explained to you a few times, the regression problem is given, is try to find the function h that maps input x to output y, just like a classification problem, except that now y is a subset of real, and then we have a notion of metric, or notion of distance. And then criteria of, the measure of success that we use to judge whether hypothesis H is good or not is based on some kind of soft measure which compares two elements in Y, not in the style of the 0,1 function that we used in the classification case, but in the style of something soft that you exploit the notion of distance. And then we looked at a few algorithms. The first one was a linear regression. Which is the most basic algorithm that uses this L2 loss, or squared error loss. So that is exactly the same as here. And then we were in the middle of, I said the linear regression is good in the sense that it has an analytic solution and it's very well understood. On the other hand, in terms of generalization, it's not performing very well. That's because it only does empirical risk minimization. So it tried to minimize an error with respect to examples in the sample, but it doesn't try to have any other term that manage the complexity of the hypothesis. For controlling the complexity of hypothesis. And we care about this is because the learning theory that we studied so far tells us, in order to have a good generalization, we need a way to control the complexity of hypothesis. So one approach that attempts to control the complexity of a hypothesis is rich regression. And we use the term called kernel-rich regression. That's because this algorithm can be kernelized. And the idea of this algorithm is we are given input. The idea is to minimize L2 norm of weight or slope. So the more precisely, this rich regression algorithm is given input, which is a sample. That is a sequence of input-output pairs. IM. And then but it solved the following optimization problem. So it tried to find, W. Yeah, sometimes we have a bias, sometimes it doesn't. I think that's because, depending on the context. So we just have a W, sometimes we have a W and B, but most of the cases doesn't really matter. It just makes our life a bit easier. Okay. When you understand this algorithm, it makes our life a bit easier. So in this case, what it tried to do is solve the following optimization problem. And then optimization problem is given like this. W is a vector in n-dimensional space. And then it optimizes something called f of w. But f of w is defined as lambda of L2 norm plus sum of i's equal to 1 to n. So the first term is about managing the, controlling the complexity of a hypothesis. The second term is about minimizing the error with respect to the sample. So this is sometimes we wrote it as L of let's not, yeah, L of this W xi and yi. Okay, so that's the algorithm. And then the key idea of algorithm is the presence of this first term. So if you just put the second term, it's essentially linear regression. But if you put the first term, that also try to minimize the size of the slope or weights, and that becomes this rich regression algorithm. And then, so just a quick reminder, this norm in this case, so this part in this case means the following. So sum of all the components of W, use K. So all the components for K is summed from 1 to this dimension n. Okay. So if later we're going to learn some other algorithm called lasso, which uses a different way of controlling the complexity of a hypothesis. So the case of lasso, instead of the L2 norms, it's going to use L1 norm. So K is equal to 1 to n, W absolute value. So this is what's going to be put in place of this L2 norm for W in the case of lasso. Okay. So the point I'm making this is just to tell you, I mean, how we manage or how we control the complexity of a hypothesis. I mean, there are many different ways of doing so, and they all have a different consequences. And it is but the rich regression make one particular choice. Okay. Right. So what we're going to, what we are going to look at now is that we will try to understand the dualization of this objective. So we will try to understand its dual. And it's because if we have a good understanding of the dual, then, I mean, essentially we can canonize this rich regression algorithm. I mean, rich regression, ultimately, it's about finding the linear functions. But if we have a good understanding, I mean, if we have a dual version of this rich regression algorithm, we can express this entire algorithm in terms of kernels. That means we are ending up using, I mean, nonlinear hypothesis via the specific kernel that we are using there. Okay, so we will dualize, just like the dualization that you see when we study the support vector machine. So how are we going to do it? So we look at, now we have to put this kernel . So what we're gonna talk about, it really just shows how, how we can use kernels in the context of rich regression. And specifically what we're gonna see is the dual objective. how we get, how we can get this dual objective. So here's a derivation of the dual objective. So we start with, it's not numbered. So we start with the original objective, which is the, so I will replace maximum by supremum of W. Okay, let's just write it to the n. We have a lambda of W square plus empirical error, which is W b of xi minus yi square. Then the first step that we're gonna do is that we will introduce some extra variable. That extra variable will express this term. So we will introduce some extra variable called psi I that express this term. So then our new objective is going to become like this: W and psi square sum of I is equal to 1 to m psi I square with a constraint. The constraint says psi I is exactly the term that is supposed to encode, subject to psi I, same as, I think, to write it this way, yi minus, it's actually W b of xi. And then the next thing that we do is that we introduce a Lagrange multiplier. We introduce a Lagrangian. So, and then there are, some of you may be familiar with using Lagrangian, some of you maybe not. But you can have an intuitive understanding about what's going on. So what we're going to do is we'll introduce something called L that take parameter W psi. And then also for each of the constraint, this is for all I and M. For each of the constraint, we will introduce a new variable called alpha I. Here are called alpha I prime, which is a real variable, and actually not just one, but we have m of them. So we have alpha prime, which is m-dimensional, and then the way we do it is we write it like this. We have the objective from the original optimization, but we also have a term that comes from the constraint. I is equal to 1 to m yi minus v of xi. And then what we do, and then we rephrase. So that's some terms that we introduce here. And then we rewrite our original optimization in terms of L, okay, Lagrangian that we introduced. So alpha prime is called the Lagrange variable. So we have supremum, not actually supremum. I think I was wrong. Yeah, we are not really maximizing the error, we are minimizing the error. So it should be infimum. Maybe I said something wrong. This is also has to be mean. So then we kind of introduce the mixed optimization. So inside the outside is an infimum, but inside we have a supremum. prime of L W psi prime. Then what's going on? So if we do it like this, then what happens is that, I mean, if the constraint, I mean, this constraint, well, actually, not this one. So we have a constraint here, which is, I mean, psi I has to be equal to the above term. I think I made a bunch of mistakes. So also has to be, this is, so alpha prime. So let me see. So we have a equality constraint which said psi I has to be equal to yi minus this inner product. So if that constraint, which say that, I mean, this term has to be equal to 0, if that constraint gets violated, so if it's either plus or minus, then this supremum becomes infinity. Okay, why is that the case? If, I mean, this term is not equal to 0, say it's like 0.5, then we can choose alpha I prime to be a very, very large positive number. So then inner supremum will increase up to the infinity. We can make inner supremum as big as possible. So from the perspective of the outer infimum, I mean, we cannot really achieve some small number because the inner supremum explodes in that case. Same thing happens when this the yi minus blah is not equal. I mean, this part is a negative number. In that case, we can choose alpha I prime to be a negative number. Then supremum, inner supremum can also explode and it can grow to the infinity. So from the perspective of the outside, I mean, essentially we failed for the optimization. So from the perspective of the outer optimization, which try to minimize the entire thing, it's better to make this yi minus blah, I mean, this term to be equal to 0, because otherwise the inner supremum will explode. So this is a way to encode constraints in terms of an optimization. If constraints get violated, the inner kind of optimization will explode. So essentially, we can't really achieve the optimization. I mean, optimal value at that point. So it's better to satisfy the constraints that we have. So that's how, I mean, that is why this equality is true. Essentially, we are encoding constraint in terms of optimization. But because L is convex, and then the L is generated from convex objective and all the constraints are linear with respect to the parameters, it turns out that we can switch the infimum and supremum. This is a non-trivial fact, but it turns out that it's the case. So we can replace supremum. And then infimum. And then furthermore, it turns out that if from the perspective of the outer supremum, I mean, so this is a kind of mixed optimization problem, but for given alpha prime, the inner supremum happens when certain conditions hold. Okay, so we can characterize when this infimum happens. So we can get more information about when this infimum happens using so-called KKT condition. So there's something called KKT condition that tells us where this infimum is achieved. And then these KKT conditions say the following. It says that if we take the derivative of L with respect to W, then when the infimum is achieved, this value is equal to 0. Okay, so if you actually calculate this derivative, then we can have, so maybe use the highlights. So we have, this term where the W appears. Another place is here where W appears here, there. So if you take the derivative and simplify, then here's what we get. We have lambda of W, 2 lambda of W is equal to summations I is equal to 1 to M alpha I prime, and then P of xi. So actually what we get is this. So this is the result of taking the derivative that is equal to 0. But if we simplify this by expressing everything in terms of W, then this is what we will get. 1 over 2 lambda. Similarly, we can also talk about the when this psi optimum can achieved with respect to psi I. So then if you take the derivative, psi I appears in here, appears here, and also appears here. So if we take the derivative in both cases, we get 2 psi I minus alpha I prime is equal to 0. Then if we simplify this and express all things in terms of, with respect to psi I, we get this equation. Okay. KKT conditions say a bit more. It also gives conditions on the alpha prime and so on, but this is the information that we can use. Okay. So this. So using this KKT condition, what we can do, we can essentially get rid of the inner impediment here. So the inner impediment can be removed because we know what W should actually look like, what also psi I actually should look like. So if we remove that inner impediment, the optimization that we have becomes like this. So we have a supremum on alpha prime, but then this supremum becomes, because W square, W is of, we know the specific form of the W. If we calculate, then that becomes sigma of, I think maybe I made a mistake. This is 4. Right. I think yeah. Okay, so we first write that this is psi I square. So psi I square becomes I is equal to 1 to M 4 over alpha I prime square. And then for the lambda W, we have a W appears twice. Here and here. So we expand, plug in the definition of characterization of W from the KKT. And then if we simplify it, we'll just write it there. So if you plug in this lambda W square becomes 1 over 4 lambda summations is equal to 1 through M. Summation J is equal to 1 through M. So alpha I prime, J prime, and then inner products of V of xi and then phi of xj. And then remaining terms, which is the term here, will become like this. F I is equal to 1 through m alpha prime and yi minus, let's expand this, 2 lambda over 1 summations j 1 through m alpha j prime, and to increase the size of the board, we have a phi of xj, phi of xi, and then there's a extra term for psi I, that is alpha prime divided by 2. So that is what we get by just plugging this definition. And we can simplify it further. So if we simplify this slightly, then here's what we can achieve. So we have supremum prime, and then we collect for sorry about this. So we first group the alphas together. So here's alpha is square, and also this one get multiplied by alpha I prime, that gets squared. So if you subtract, combine all of them together, we end up with minus alpha I prime square 4. And the second terms, we collect yi's. This yellow. So we collect yi's, and that becomes sum of i's 1 through m, phi prime, phi. And then finally, we get this alpha I prime, alpha j. So we put in this term and essentially this term together. So then what we get is that we have minus 1 over 4 lambda, and sum of I is equal to 1 through m, j is equal to 1 through m, the alpha I prime for j prime. Then we will use kernel, introduce kernel here, xi, xj. So here, the k of xi, xj is defined as you expect. It's defined to be inner products of phi of xi and then phi of xj. Okay. So this is a form that the dual form that of the kernel ridge regression. Expressed in terms of a kernel k. But we will analyze this a bit more. Okay. So how are we gonna do? Extend the board a little bit more. So what are we going to do? So we will write, so view notation here. So we will write alpha to be a vector of alpha i's. So it's alpha 1 to alpha m. So m-dimensional vector alpha prime. And okay. Now let's do some Okay, let's follow the textbook and make a few changes there at the same time. So we first introduce alpha I. That is going to be 2 times square root of lambda alpha I prime. I mean, this reparametrization makes things in a form that that makes what's going on a bit more clear. So then optimization will be expressed in terms of alpha I, and then this second, we will write all the things in terms of matrices. So we have an alpha that's going to be alpha 1 to alpha m. It's a vector of size m. We'll have a matrix K, corner matrix, whose ijth entry is going to be K of xi and xj. And also we're going to write a vector y, which is y1 or 2y. So if we do so, and then the final goal can be now written as follows. It is a supremum over alpha, but then the first term is written as minus lambda alpha transpose of alpha. In other words, inner products of alpha with itself plus this part will become 2 times square root of lambda alpha transpose y. The last bit is going to be written as simply alpha transpose k and alpha. Although I didn't really go through the computational step, I mean, if you just apply this reparametrization, it can be written like this. So, I mean, we're gonna write these things. I mean, let me just do a bit more manipulation. So typically, this is written like this. Supremum of alpha to square root of lambda transpose y plus and minus alpha transpose and k plus lambda identity matrix. So, I mean, these two are equivalent. And then this formula is going to be written as, we'll call it as a G of alpha. So dual optimization is really, I mean, refers to dual version of kernel-rich regression really refers to this problem. And maybe just don't go that much. Yeah, so this problem refers to the dual optimization objective of kernel-rich regression. And if you compare this with the primer version, so then it looks have something very, very similar. The primer version, I didn't really show it to you. So the analytic solution for the primer version have the following form. So, okay. Purple. So if I compare this with the primer versions, then at least you can see something similar appears there in the primer versions. And maybe I'll not talk about this here, and then let me talk about the solution. Okay, so this is the optimization objective, but then we can say, but it turns out there's a G of alpha here. It's pretty good. I mean, it's a differentiable function, and it's a quadratic differentiable function, and alpha is unconstrained. So we can find its global optimum by taking its derivative and setting it to 0. So if we do so, then we can actually get an analytic form of the solution. So if we take the derivative of G of alpha, and say it has to be equal to 0. So then this g of alpha, I mean the derivative becomes, just the calculation, derivative becomes c, this becomes minus and plus 2 lambda y minus 2k plus 2 the lambda identity matrix alpha. So if we set this to be equal to 0, so then what we get is that we have a, say, alpha has to be of the following form, should be lambda of k plus lambda I inverse 1. So we can have this type of analytic form. Now, right. So then something that I want to compare. I mean, this is an analytic form for alpha. And we also have a analytic form and then the analytic form for the primer case, if I give you, I mean, remind you, it was the following form. Say that W was X transpose plus lambda I X Y equals, I mean, it has an inverse like this. Now, for then there is something that I want you to notice here. And if you have a XX transpose, I mean, so X is a matrix which have a feature V of X1, V of Xm. So if we compute X and X transpose, so this is the dimension is R to the number of features is corresponding to the row, and then the number of data points is corresponding to M. So if you compute XX transpose, that's going to become a matrix essentially describing how features are related with each other. R to the N cosine. On the other hand, K is really, it becomes X transpose. Okay. So if we compute the K, I mean, the actual definition of K, I mean, you can compute this. If you compute this, this is equal to the XX transpose. So then this is a matrix R, the M cosine. So the W and alpha are, in a sense, very closely related. In one case, we are computing XY and then apply very similar kind of inverse, but in one case, the inverse of that we apply is a phrase in terms of a feature matrix. So on the other hand, in the case of alpha, the inverse we are applying is phrased in terms of the relationship between the data points. Okay, so the difference appears in the dimensions that here. So one case we try to say how two features are related. We compute it by we compute it by I mean calculating this XX transpose, and then actually this has to be X transpose of X. So on the other hand, to talk about the relationship between two examples in the sample, then we are computing in some stage dual version here. So now from this analytic form, we can actually calculate the the hypothesis, optimal hypothesis that uses alpha. So if we do so, it has the following. So the hypothesis should be of the form h of x should be inner products of w and p of x. So if you compute here, then the KKT condition we talked about, it gives us, it says that w should be equal to 1 to m. But I mean, because of the reparameterizations, there is some slight difference. Yeah, it was, let's write it here. W was 1 over 2 lambda to m was alpha I phi of xi phi prime phi of x. But this alpha I prime, we reparameterized it to be 2 square root of lambda I phi of x. But these inner products can be written now as corners applied to xi and x. Then if we simplify a little bit, this becomes square roots, and then get rid of 2. And this is the form that we ultimately obtain from the summation I to m alpha I k of xi and x. Okay. But now let's write it as a matrix form. Then if you write this as a matrix form, it is square root of lambda, and it's an inner products between, I will write it as a k x x1 to m. So this is really, I mean, the vector that we construct by, applying k to x1, x, x2, x, and so on. So that's what it's written like it's here. And then the other one is just vector alpha. Now we plug in this vector alpha that's given here. So if we do so, then here's the final outcome that we can get. The square root of lambda will cancel with each other, and then really we have k x1 to m transpose multiplied to k lambda x inverse n1. So that's the hypothesis that that we get in the kernel-rich regression. So what does intuitively means? It means that in order to make a predictions on x, so in order to make a prediction on x, you first compute its relationship with every examples in the sample used for the training. So k x comma x1, you compute the relationship between x and x1. K x comma x2, compute the relationship between x and x2, and so on. But then the others, this is in a sense a kind of normalized version of the result or the output that's supposed to happen for x1 and up to xm. So it's a normalized version of the output, and then this k, this first vector tells us how we should combine these outputs together. So pictorially, although this is not it's just some picture that comes to my mind. In some sense, this hypothesis H is a bit like it remembers some values for x1 to xm. It computes some value. Okay, that corresponds to the vector is computed here. So it computes some processed value y1 prime for x1, processed value ym prime for xm. Okay, so that's different from y1 to ym. It's something computed by multiplying this inverse matrix to y. And then afterwards, whenever new data point x comes in, then you compute the relationship between x and x1 by computing the kernels kx x1. Compute also relationship between x and xm by computing the kernel kx and xm. Now, once we compute these values, it now take the average of all these y1 prime to ym prime based on this kernel value. Okay. So the final outcome then becomes summation of k x xi yi prime I is equal to 1 through n. Okay. So it's a bit like for every example in the sample, we remember something. The hypothesis remembers something, and whenever a new point comes in, then you try to compute how we should combine what it remembers. Okay. Okay. So that's the kernel-rich regression and its dual version. And there are two other comments that I want to make. The first comment is that now so far we ignored bias term B. So how should we include this bias term? So very simple answer for this is the following. We say that our feature map. So we think about new feature map. So that compute the old feature map, but it also puts some extra term 1 here. Okay. So then when we compute the weights, our weight is going to be now a vector in the n+1 dimensional vector. So then if this extra coordinate in the weight will take care of this extra component in the feature map. Okay. If we use kernels, then what should we do? If suppose we use kernel k, so if this feature is implicit, then so we have a kernel k for phi. Now how should we construct the kernel k prime for phi prime? It's quite simple to compute the kernel k prime. I mean, if you think about the inner products obtained using phi prime, it's just inner product obtained using phi plus 1 because the extra coordinate is 1. So for k prime, we can just use kx and x prime, k x prime plus 1. Okay. So that will give us the kernel for phi prime. So even when we don't know how to compute phi, we can do this. Now, so this is an easy way out, but there's a catch about this approach. What's the catch? Catch is that we're gonna minimize. So our optimization objective will have prime square. So in some sense, we are not just minimizing the weights of our hypothesis about the slope of our hypothesis. We also minimize the bias, the size of the bias. So this is same as lambda of w square plus lambda b square. Maybe this is what we want. So I mean, this is what's going on. And maybe we are okay with this because this is exactly what we want. But sometimes, I mean, you don't want to include this extra term. So then, this approach, to think about how not to include this extra term, make things much more complicated. So that's one comment. And the other comment is that now, whenever we use this approach, now if you think about the weight W, this weight W is typically very dense. So in other words, if capital N is like say 100, so then the W is going to be a 100-dimensional vector. Then it's not the case that like a majority of them is equal to 0. So the majority of them will contain some values. Okay, they will be small because of our regularizations, but the extra term that reduce the model complexity, but there will be lots of them. So very lots of small numbers. Some application, that's not what we want. We want a solution. We want a sparse solution where the majority of the coordinates in W are 0. So then the question becomes how we can modify, well, how we can come up with a new version of this algorithm which achieves this sparsity. Okay. So what I'm going to explain to you maybe now and then maybe the next Tuesday are two approaches to achieve the sparse solution. Okay. So that brings us to the next part, something called support vector regression. So as I said, the one objective of support vector regression is to achieve a sparse solution. Well, maybe goal is better. What is the goal of this algorithm? You want to have a sparse solution or sparse hypothesis. Sparse in the sense that the weights, or the slope term W will have a majority of the coordinate will be 0. So that's what we want to achieve in this support vector regression, abbreviated as SVR. And also we want to have some good generalization by having a term that controls the complexity of the model. So what should we do? And the idea of support vector regression is the following. So the idea is that now suppose we have a bunch of data points in two-dimensional space. Suppose we have a bunch of data points like this here. So then our algorithm came up with the hypothesis, which is a line that goes like this. And then so the idea is to change the empirical error in the following way. So if beforehand the empirical error was measuring the distance between what our hypothesis say and an actual point, and then that distance maybe usually was the square distance. Okay, well you can say also means the squared error is the one that we have been using so far. But the idea of support vector regression is that if a point is quite close, so data point is quite close to the line. So suppose we put some epsilon gap, so like this, above the line, and also another epsilon gap below the line. So then some of the data points will become quite close. So for instance, if you look at data points like this one that is within this epsilon distance. So this is epsilon plus epsilon. So epsilon distance, this is also epsilon distance and so on. And these are the close points. And then the idea of support vector regression is that let's not penalize all these things that's close enough to our prediction. Only penalize the one that is far away, that is far away, away more than epsilon. So that's the idea of support vector regression. And then to implement this idea, the support vector regression uses very, somewhat strange notion of loss. So it uses L epsilon loss. So epsilon is a hyperparameter, whose value should be greater than 0. So that take 2y's and then tell us how much we should penalize this. But then they say the following: L epsilon. He uses x of 0, y minus y prime minus epsilon. So what's going on? So you say that if y and y prime are not the epsilon far away, I think the distance should be written like this, epsilon. So if y and y prime are not epsilon far away, then the penalty that we're gonna give is equal to 0. And if y and y prime are more than epsilon far away, then we're gonna discount epsilon much, and then we only penalize the rest. Okay, so this is subtracting epsilon means that if it's close enough, then we are not going to worry about this. And it turns out if we do so, we can achieve often the sparse solution, and also the behavior of the regression algorithm that's derived from this loss is very much like a support vector machine. So that's why it's called support vector regression. Okay, so how to do this? So let's realize this idea. And the optimizations, so the story is the same. We are given a sample, which is the sequence of XY pairs. And we solve some of this algorithm. Solve the following optimization problem. So as the problem is solved, this one is minimize. Quite similar to corner-ridge regression, it minimizes the. This time we think about the weight as well as bias. Minimize this term, but then so instead of using lambda, it uses a c, but they are essentially the same thing. So we have a terms to manage the complexity of the model. But you can also say we regularize the model. The other term is for the errors from prediction error or empirical error. But then for empirical error, it uses this L epsilon. And this is also often written as epsilon. Okay. So in the textbook, that's the notation that they are using. So we have, you can write it yi p of xi. So we compute the difference between the ground truth, which is yi, and the prediction of our model, so which is this inner products and sum, and take the difference and take the absolute value, but we cut it at epsilon. So if this difference is smaller than epsilon, it becomes 0. If it's greater than epsilon, we subtract minus epsilon. So using, instead of L2, the squared error, we use is just, the L1 error, so we don't square it. And also we are using epsilon. These are the two key differences of this algorithm. The use of this at the absolute value instead of a squared error, it is not so significant. We can still use a squared error, and we will actually think about it. But the use of epsilon is what matters the most. So then now instead of solving this, we solve the following version. I mean, this is because of the absolute value and epsilon. I mean, sometimes it's not immediate how we can apply, in some sense, off-the-shelf solvers to this specific optimization problem. But this problem can be rephrased as follows. So we have a WB, and we have psi and psi prime. And this is W square, C summation I is equal to 1 to m psi I plus psi I prime. Now you can see that in the optimization objective, we are not using anything strange, but this optimization becomes more complex. It will have a constraint. The constraint says the following: psi I has to be greater than 0. Psi I prime also has to be greater than 0. And psi I is greater than weights b of xi plus b minus I minus epsilon. Okay. So if the distance between our predictions and yi is, I mean, it is smaller than epsilon, this entire thing will become minus. What I just wrote become minus. So it won't affect the psi I at all, because psi I already has to be greater than 0. But if it's greater than the right-hand side of this inequality that I just wrote is greater than 0, so then we have to grow the psi I to match it up. Okay. Then also for psi I prime, we have something similar. But for the other direction, so if you consider the case where yi is greater, b of xi plus b minus epsilon. So we have this type of constraint for all. And then the idea, I mean, so in some sense, you saw some similar idea a few times. Whenever we have a constraint, I mean, or some complicated function, we can often get rid of that complications, or we can get rid of some constraint by rephrasing things in terms of optimization. Okay, optimal value, whenever something is optimal, it will automatically satisfy the constraint, or it will automatically kind of match with a more complicated scenario with more complicated function. So that is what's happening here. I mean, one way to understand what psi I and psi I prime is really, I mean, it's a bit like this. So psi I mean, if actually, I think maybe just using. So we said that, I mean, so this loss, we mean have a, when you compute this loss, what we are computing is that we take the difference between these two and also take the difference in the opposite direction. And if it's greater than epsilon, and then it's going to create a loss. And because, I mean, the red part that I just highlighted, I mean, there's two red part here, this part and this part. I mean, these two red parts are essentially, one is the minus of the other. if one of them is greater than 0, the other should be smaller than 0. Okay, so suppose the one on the top is greater than, it's a positive, but if that number is smaller than epsilon, it's not going to constrain psi I at all. Okay, so it means psi I will be only constrained by the first constraint, which is greater than 0. However, this term that you see here is greater than 0. So that means the highlighted part is greater than epsilon. So our hypothesis and the ground truth is far more than epsilon apart. In that case, that's going to mean this row bound to get activated in some sense, and this activated lower bounds. Yeah, so this activated lower bounds will will force that this psi I has to be, the epsilon subtracted distance between the predictions and the ground truth. Okay. And now, because psi and psi prime can be any non-negative variable, we can choose any psi prime. But because we are solving this optimization problem, we have to minimize when optimum value happens. In that case, which is, this part is greater than epsilon, what we're going to have is psi I will measure this loss. Psi I prime will become equal to 0. Okay. And in opposite situations, psi I will become 0, and psi I prime will measure the loss in that case. So these two things becomes equivalent and an optimal value. These objectives are minimized. Okay. But once you rewrite the entire formula in the form that's written below, so then the formula that's written below is a standard convex optimization problem. It's a quadratic, so-called quadratic programming, which is a convex optimization problems, which can be solved by an off-the-shelf solver. So solving this directly is not it's not something it's not easy, but it's not too difficult either. You can just use off-the-shelf solver to solve this optimization problem. Now I have about 5 more minutes, but I feel that now I want to talk about dualizing this, but then I think it will make story. I don't think 5 minutes is enough. So on the other hand, let me talk about something else. No, I said the most important bit about this support vector regression is the use of epsilon. Okay. So this epsilon is the most important part. So if the distance is smaller than epsilon, we're gonna ignore it. Okay, so that's the most important part. Now, but for this version that I'm presenting to you, it uses just, when you measure the empirical error, it doesn't square it, but squaring it is not problem at all. So we will look at another version. In the squared error version, we'll have subjective B 2 C summation I is equal to 1 to M U V of Xi like this. squared version. And actually, I didn't really double check doing so exactly correspond to putting square here, but that's possible. I mean, I didn't really do this, but the point I bring it up is because, I mean, if you do so, what I'm going to tell you maybe in the next Tuesday, which is dualizing this algorithm and getting a kernelized version of the support vector regression. Almost the same idea applies. And when you apply this, we get a one algorithm for the without squared error, the other algorithm with a squared error. The algorithm with the squared error can be understood as a generalization of the kernel-rich regression. Okay, so that's it for today. And as I said, we are not going to have a lecture on this Thursday, and we will resume on Tuesday next week. Okay, so thank you very much.